This is lesson 3, and the starting thing to look at is the background of the title slide here. If you look closely at these rocks, you'll notice there's a strange kind of swirling pattern on them. That's because the pattern on them is actually a fossil. We can get patterns like this in metamorphic rocks, but if you were in this area and looked at them more closely, you would recognize that these are actually fossils and not some type of metamorphism. The actual fossils that these are something called stromatolites. And stromatolites were some of the earliest fossils, or actually are the earliest fossils that we have. They can be as old as 3.7 billion years old. And the rock record has preserved them. Basically, a stromatolite is a bacterial mat that is blue-green algae just kind of piled up, intermixed with sediments. So here you're looking at what stromatolites look like after several millions or perhaps even billions of years worth of erosion on these rocks. You can see the layers and the swirl patterns. They're all characteristic of stromatolite fossils. And I should say that this is also an interesting fossil because these particular bacteria still do exist today. So stromatolites are bacteria that are among some of the earliest life on this planet that's preserved in the fossil rock record, and these bacteria still exist today. Later in this presentation, we might talk about animals, the oldest animals that are still preserved, but as far as bacteria, the oldest organism that's preserved in the rock record on this planet is this blue-green algae, also known as a stromatolite. We're going to discuss some things we went over before as a quick review, but an important one. First, we'll talk about isotopes. I introduced you to isotopes probably in lesson 1, and if you recall, isotopes are just basically any element from the periodic table whose atom has a different number of neutrons. The atomic weight changes, but not the atomic number. Other than that, it acts very much similar to the regular way the element would behave. Some of these isotopes can be radioactive, and it's these isotopes we're specifically interested in with geology because we can use what we learned about half-life to try and determine the age of the rocks that these isotopes are within. And if you've forgotten about that, we're going to touch on half-life and give you a quick review in just the next slide here. But that is pretty much it. You don't change the number of you don't change the number of protons, you don't change the number of electrons, you're just changing the number of neutrons. And almost every element on the periodic table, with the exception of I think about 8 of them, have different isotope values. For the visual learners, here you can just see physically what it looks like. We have carbon as appears on the periodic table all the way to the left. Carbon's, two of carbon's isotopes are shown here. We have carbon-13, in which we throw in one more neutron, and we have carbon-14, which is radioactive and used in scientific dating all the time, as we learned. Carbon-14 is just adding in 2 more neutrons. So we haven't changed the element at all, we've just changed the number of neutrons and the weight in doing so. So this was an interesting question. The AAA ball team that is present in Albuquerque, yeah, the actual name of the ball team is the Albuquerque Isotopes. And Homer Simpson was on there because the idea kind of spurred from an episode of The Simpsons. If you've ever watched The Simpsons cartoon, Homer Simpson works in a nuclear power plant, and in one of the episodes they played baseball, and the name of the team was the Springfield Isotopes. So fast forward to real life, the Albuquerque newspaper was putting a poll out to see what they should name the newly acquired baseball team at the time. And names fluctuated wildly, but one of the most popular names in the poll was the Albuquerque Isotopes. And it actually won first place in the newspaper poll, and they pitched it to the people who owned the ball team. They did a lot of consideration on this, and they were possibly not going to go with it, but then given the fact that Albuquerque, New Mexico is actually home to the Los Alamos National Laboratories and some other laboratories that do nuclear research, it was also where they did some preliminary testing for the atomic bomb and kind of devised all that during the Second World War. So given the deep history in nuclear and isotope research in Albuquerque, they decided to stick with that name. Going back to radiometric dating again, just a brief refresher. It's all dependent on the concept of half-life with radioactive isotopes. Radioactive isotopes are spontaneously giving off energy and breaking down. As they do this, they approach something called a half-life. The half-life value is different for each and every element that's on the periodic table, or I should say each and every isotope that's on the periodic table. In the case of, we looked at carbon-14, that'll decay to one half-life in about 5,730-ish years. In the case of something like potassium-40, it's a lot longer, and it will decay and reach its first half-life after about 1.25 billion years. So that's very interesting that they all have their unique values, and that's what's going to differentiate these isotopes and make some more useful in geology than others. But essentially what's going on here is when these isotopes start to radioactively decay, they have the parent material, which is the original radioactive substance, that's converting to what we call a stable daughter product. The stable daughter product is often a new element or an isotope of the same element but a different number. Either way, you're getting something new created, and the new daughter product created sometimes can be radioactive, but it's just more simple if you think about it being stable. So I'm kind of paraphrasing a lot here, because there's certainly, when you get into uranium dating, there's chains of radioactive decay that can occur, and chains of different what we call transmutations going on, where one isotope is converting to another and another. But it's best to simply think of it as, for the purposes of this class, think of it as a parent is the radioactive isotope, and the daughter is a new stable product that's being created. And the way that half-life works is every time you reach one value worth of that particular isotope's half-life, you then have 50% of the original radioactive parent remaining. The only place where you're going to have an equal amount of parent material and daughter material is only at the first half-life. And once you get past that, when you reach your second half-life, you start having a lot more daughter material and a lot less parent material, ultimately going down and down and down until we have relatively no parent material remaining whatsoever. It's all decayed and radioactively decayed and transmuted into a different isotope. So this is just a diagram showing you what we call the decay curve. This is more of a visual for you. You can see the red circles up here illustrating exactly what I mentioned. As we go through each half-life, we go further down this decay curve. So the gray circles and the red circles illustrate the point very, very nicely. If you look over on the left-hand side, we start at time 0 when pretty much the isotope has just been incorporated into a crystal. And what happens here is we start moving our way towards our first half-life at whatever value of time it takes to get to that first half-life. Whenever we reach our first half-life, you can see that we start to continuously decrease the amount of red circles and increase the amount of gray circles. Here, again, the only time you have an equal number of gray and red circles or an equal number of parent material and daughter material is only going to be at half-life number 1. Once we get past half-life number 1, or as we move further towards the right on this diagram, you're going to see that the number of gray circles representing daughter product is much more increasing, and eventually the red circles representing the radioactive parent material are going to run out. We don't see that here, but we haven't really gone far enough. Maybe it'll occur towards half-life 10 or something like that. But it's going to, this decay curve is eventually going to hug the y-axis, or excuse me, the x-axis, the bottom line there, and eventually it will just all completely transform into a different isotope. This purple slide is just a quick reference one. I've showed you this before. It's just so you can flip back through your notes and have an idea of how old or how far back it takes to get to one half-life of a particular element. The most interesting one here is probably going to be rubidium-87 to strontium-87. It takes 48 billion years for this to happen. So we haven't even seen one full half-life of rubidium to strontium conversion at this point, and humanity may never will. It's insanely long. Some people might be wondering how we get that. We see how much decays in minutes, seconds, hours during a day, and we just computer mathematically model it out, and that's given us this age, even though no human has lived that long, or will live that long perhaps. The next thing we have here is the chart of the nucleides. Now, the chart of the nucleides is something maybe brand new to you. It's usually not shown in an introductory chemistry class, or probably not shown in your high school chemistry class. But what the chart of nucleides is this chart on the right-hand side, and it is a diagram that's similar to the periodic table, but in this case, it's showing all of the isotopes for each of the elements on the periodic table. The black spine down the middle represents each of the elements from the periodic table, and the different colors to the left and right of that black spine are different isotopes that are created from different types of radioactive breakdown, which we'll talk about in a few minutes. A couple of important things to note though: while radioactive elements are very handy in geology, usually everything below element number 83 is going to be not radioactive, and everything above tends to be more radioactive. Whenever you do have an isotope undergo radioactive decay and go through all of its half-lives and convert into an entirely different isotope, we actually call this process transmutation. And it happens quite a bit, especially if we think about uranium dating, which we're going to look at in just a minute here. The other thing, just to focus on this, we'll be talking about these, but the different colors, I mentioned they represent different types of decay. The key for that decay is in the lower right-hand corner here. You can see there's alpha, beta. Not listed on here is gamma. That's another different type of decay. And we'll talk about fission decay in a bit. Fission, F-I-S-S-I-O-N, not fusion. So now we're going to show you, there's a lot of chemistry going on here, but try not to freak out about this. This is just to show you how the decay chain works. As I mentioned, certain isotopes don't just immediately convert or transmute into the next isotope that they're going to create. Uranium-238 is a beautiful example. Uranium-238 actually takes multiple steps and converts to many different things over very different half-life times, and ultimately works its way to lead-206. So if you look at this diagram here, a couple of things to notice. First, above all the arrows, in this particular case, there's alpha and beta symbols. And the alpha and beta just represent what kind of decay is going to occur. And below the line, we have number values. Those number values have symbols next to them. The symbols represent units of time. If you look at this, you will see that the units of time are all different. For instance, the first one, uranium-238, changes to thorium-234 isotope over 4.468 times 10 to the 9th years. That's going to be a very, very long time. That's probably millions, if not billions of years for this change to occur. And the interesting thing here, though, is that's probably the longest one you have. If you go further across and scan some of these values, you'll see that some of these occur within minutes, hours, a day, and the fastest one is actually going to be, I think it's polonium-214 to lead-210. Through this alpha decay process, it takes 164.3 mu second. Mu stands for microseconds. So faster than you can even snap your finger, this decay process converts almost all of the polonium to lead-210 isotope. The one type of decay that's not shown on there is going to be gamma decay. We'll talk about gamma decay in a little bit. It usually isn't really related to transmutation so much as it's kind of a cooling down effect, if you will, afterwards. We'll look at that. Okay, so you just saw a video for Rutherford's experiments. Basically, he bombarded a screen with radioactive wavelengths, And with that radiation, he was able to document that not all the radiation was equal. Some of the radiation was curving upwards with more positive charge. Some of it was curving downwards with negative charge. Some of it was just straight going through. He was basically discovering, as the video said, the different types: alpha, beta, and gamma radiation. So we're going to talk about each one of those now. We're going to start with alpha decay, or alpha radiation. Alpha decay is when you have radioactivity occurring with an isotope that is spontaneously giving off energy, but that energy given off releases 2 neutrons and 2 protons. You can see it marked over where the alpha symbol is. In some scientific texts, they'll actually have a helium symbol there, because if you look at it, 2 protons and 2 neutrons is exactly the nucleus of a helium atom. So I'm just going to go with alpha because it's easier to talk about here. But the decay process here is so excited that it basically throws 2 protons and 2 neutrons out of the system. When it does this, the isotope is going to transmute. And if you think about what we talked about back during, I think it was lesson 1, I might have asked you what happens if you change the atomic number. And the answer to that, if you change the atomic number, you're changing the element. When we deal with isotopes, we're changing the number of neutrons and changing the atomic weight, but we're always in the same element. But if you tamper with the protons, you're going to have a different element at the end. And in this case, we sure do. We tamper with the protons and the neutrons. Not only do we get less atomic mass, but we got even less atomic mass because we've also jettisoned and thrown out 2 protons. So what this is going to result in is where whatever element you have of a particular isotope, you're going to bounce back 2 atomic numbers on the periodic table because you've gotten rid of 2 protons. Basically, this creates a net positive charge, as you see there in the bullet point, and that was what was attracting the radiation towards the negative symbol in the last video. But that is one important type of decay. So we saw this, a lot of this occurs when you have uranium going into lead, uranium-238 to lead, that we saw just a minute ago. Another type of decay that was happening in that same chain reaction of radioactive decay was beta decay. And beta decay can sometimes be called electron decay, or if you see a symbol with it, sometimes they'll have the electron symbol, the E with the negative sign over it. And the reason for this is the way beta decay works. You get the nucleus so excited that it expels an electron out of its system. And when it does that, in order to compensate for that loss, a neutron will change into the proton. If you get rid of the electron, the neutron will kind of substitute in as a proton. Now it's got more positive charge going on. And so with this, you're actually going 1 element or isotope forward on the periodic table instead. So this is the opposite direction of where we went with alpha decay. And with this creates kind of a slight, negative charge that draws it towards the positive end, like you saw in the video there. And so the key thing here is just we're going 1 element kind of to the right, or all the way down and to the right if you're on the end of the periodic table. There is one last type of radiation, and that is gamma decay. Gamma decay, you have the symbol there, the Greek letter gamma, and you can see it's shown as a wavelength here. Basically, when you get to the electromagnetic spectrum and radioactivity, you can think of it as a photon, which is kind of a wavelength or a particle. And with this, gamma decay usually occurs when there's a lot of pent-up energy right after an isotope has undergone alpha or beta decay. And the important thing with this is there's no real atomic mass change going on here, but this is some of the most dangerous radioactivity we can have. It's short wavelength radiation coming out at very fast paces from this type of radioactive decay. This is the stuff that creates cancer and causes radiation sickness. We want to avoid this by all means. I might have shown you this before. This is the electromagnetic spectrum, and this is just to show you what the different wavelengths are. And you can see on the right-hand side, we have this gamma radiation. Very short wavelength, often high-frequency radiation, and that is the stuff we want to watch out for. The length of the individual energy wavelengths is about the size of an atomic nucleus. You can also see as we progress to the left here, you're getting more tranquil, less damaging radioactivity to us. We have the sizes for X-rays. X-rays can be dangerous, but for the most part, if we have them in moderation, they're not that bad. Ultraviolet rays, those are the ones that hit you during the summer and give you a sunburn. We can't see them with our eyes. The thing I should point out here is down the bottom you have the visible light spectrum and basically that rainbow. It's actually the visible light spectrum and a little bit beyond that because the infrared is kind of shown on there. These are basically, we can only see Roy G. Biv, if you will. So from red to violet are the colors that our eyes can see because there are certain wavelengths. Our eyes aren't attuned to pick up the ultraviolet radiation, but we do have modern day sensors and equipment that could do that, but that's why when we're out during the sunny days, we really don't see the waves hitting us, even though they're causing a lot of damage. What we usually see is red skin hours later, or if you're lucky, you're going to be tan hours later. Again, you want to be absorbing ultraviolet radiation in moderation. You can see as we keep going to the left, some of these waves in the infrared spectrum are as big as the tip of a pin. If we get to microwaves, the same stuff that heats your food every day and the same stuff that we use in radio telescopes, that can be anywhere from the width of wings from a butterfly to maybe the height of a human. And the radio waves that you get in your car every day, your car antenna, you hear the radio, those waves are very, very super long. They're actually very, very safe for us, and the wavelengths are taller than buildings in some instances. So those are the different types of waves you have, and the most dangerous stuff, the gamma stuff, is shown here over on the right-hand side. Now, another way to think about this is thinking about what we need to do to shield ourselves from these different wavelength types. If you have, or I should say these different decay types. If you have alpha decay is radioactivity, but it's relatively simple to stop. You can do it with a sheet of paper. Alpha decay particles will not pass through a sheet of paper. It's very hard for it to even pass through your skin, so it doesn't really do much damage. We then have beta decay. Now, beta decay is a little bit more punch than would be alpha decay, and it will penetrate through a paper, but it will not penetrate your skin, and it won't penetrate aluminum. Now, this diagram doesn't show how thick the aluminum is, but given that it won't penetrate our skin, I would say that maybe even a flimsy sheet of aluminum foil might be enough to block beta decay, but I'm not a nuclear physicist, so don't quote me on that one. But needless to say, aluminum will stop beta decay. Now, gamma is the most dangerous, and you can see why here. If you look, gamma decay is so powerful and energetic, it's going to go through the paper, it can easily pass through aluminum, and you actually need lead to stop it. Now, lead thickness is also not written here, but it does show a relatively thick lead sheet just on the imagery. And I would say that when I've heard about nuclear fallout shelters and that, you need a pretty thick lead, I mean at minimum maybe 6 inches worth, I think I've heard, of lead to block nuclear radiation of the gamma type. The reason we use lead is because it is the highest atomic number substance that is not going to be radioactive, so it has potential to really absorb some of these gamma rays. So, if you're ever forced to be in a bomb shelter, you're going to see that they line those with lead. Now let's talk about which rocks can be dated. And the preferred choice of most geologists is most likely going to be igneous rocks, because their story is they just cool down and hopefully they're preserved in a section of the Earth's surface or just underneath the surface where not too much is going to happen to them. You won't have too much physical abrasion. You won't have too much heating going on. So I would say that igneous rock types are one of the main types of rock we look for when we're doing radiometric dating. That being said, you can date other substances. You can date metamorphic rocks. Metamorphic rocks are tricky to work with, though, because when you're looking for the decaying radioactive isotopes in there, if the metamorphic rock undergoes too much heat, it can actually allow the crystal system to open and release parent and or daughter isotopes and give you an incorrect age. So you got to be careful with that. If there's too much pressure, it could also cause fracturing in the crystals that could also release the parent and daughter materials, causing an offset in the age. And lastly, we have, just going back for a sec, so I would say if you're using metamorphic rocks, you need to take very, very careful precautions that you're using metamorphic rocks that have experienced very low temperature and very low pressure. Lastly, we have sedimentary rocks. Sedimentary rocks are basically rocks that form from broken down previously existing rocks. So they've undergone a lot of physical and chemical weathering in the first place. And that's very suspect when you're trying to measure the radioactive parent and the stable daughter material that's in them. There's a lot of possibility for cracks to develop and to lose a lot of the daughter isotope, parent isotope, and it can be a little bit of a tricky situation. That being said, though, there are some circumstances where even in sedimentary rocks, certain crystals have been very well preserved, and we might not be able to use the majority of the rock, but certain very resistant crystals we can use that haven't broken open or experienced chemical or physical weathering to great degrees, haven't been reheated. We can use those to try and figure out the age of rocks. And matter of fact, the oldest rocks that are present in the world, that was one of the ways that they determined the age, through a single crystal that was preserved. Just another visual for you again. This is how the radioactive isotopes get entrapped in the material. You have lava or magma, and in that lava or magma are naturally occurring radioactive isotopes. They basically get entrapped in crystals as the lava cools, and excuse me, lava is above the surface, magma is below. So basically, if it's below the surface, these radioactive isotopes get trapped and encaged in crystals of different minerals below the surface. Give it millions or billions of years, and all of a sudden, erosion whittles its way down to the top of what used to be the magma chamber, and you'll find it then. Or in the case of what you're seeing here, the magma is exploded out of the surface of the volcano, converting to lava, liquid surface molten material, and then it solidifies into a rock at the surface, making it easier for geologists to try and find it years later. So you can see in the very last picture, all of that potassium-40 has been preserved in these crystals, but has started to convert itself into argon-40. This geologist digging can then find that, undergo radiometric dating techniques for it, and figure out how much potassium-40 exists compared to how much argon-40 exists, and based on the age of the half-life, determine how old this rock is. Now, what minerals in specific do we use? That's a good question. There are a wide variety of minerals. Geologists are always trying to use different minerals to determine things. It's not so much what minerals we use as to what their chemical composition is made out of. So you can see over here in the diagram or in the slide, there's thorium, uranium, potassium, rubidium, samarium. These are some of the more popular isotopes we look for. And the long story short here is any mineral that contains these in their chemical formula or symbols can be used. Obviously, uranium is a lot harder to track down minerals that contain that, but it can be used. So as long as the mineral's chemical formula contains one of these, it can potentially be used for radiometric dating, assuming that it hasn't been profoundly chemically weathered to the point where things break, or it hasn't been profoundly reheated to the point where the parent and daughter isotopes escape and reset the age to something incorrect. We want the purer the mineral, the better. That pretty much just goes with what I said. And the last thing is, this is one that's not really mentioned too much in the textbooks, but with whatever rock you're going to use, you need to make sure that it has an ample supply of whatever mineral you're looking for. I'll give you a real-life example of when I was in graduate school. I was working on a rock trying to get the mineral apatite out of it. And I spent 2 days breaking down about 2.5 pounds of rock, and in the end, all I was left with was about 8 apatite crystals. I had to dissolve some things in acid. I had to magnetically separate things, smash things into powders, or not powders, but smash things apart with really small, fine grains. And in the end, all I got for that hard work was 8 grains of this apatite, and that's way too few. You probably want at least 20 to 50 of these grains in the sample in order to use it. So whatever rock you're using, you want to make sure that it has plenty of minerals, because basically in my scenario I would have had 8 chances, and that's not really good. Imagine if some of those or half of those were damaged. That wouldn't even give me accurate ages. So just make sure that there are enough is the other thing to mention here. Now I'm going to show you some different minerals. These are 3 different minerals. We have orthoclase, muscovite, and amphibole. While these minerals all have incredibly different properties to them, different colors, different cleavage types, different crystal habits, different hardness, all of these do have one thing in common, and that's if you look at the chemical formulas that are below each of the pictures, you will see that potassium is somewhere in there, usually towards the front. And if it has potassium, there's a very good chance that it's going to have potassium 40. So all of these minerals could be used to radiometrically date a rock. Let me give you another example of different minerals that we can use to find elements or isotopes. In this case, uranium-235 isotope and uranium-238 isotope. We can look for those in any of these minerals. But if you look carefully, you're going to see there's a problem here. Go ahead and look and see if you can figure out what the problem is. Okay, the problem is this. We're looking for uranium. 238 or 235, which means the chemical formula of the particular mineral should have uranium in it, or the symbol U. There's only one mineral on there that has U in it, and that's going to be uraninite, which is a uranium oxide. And so why do we have the others there? Well, again, this goes a little bit beyond most of the basic chemistry that you've probably learned, but the other 4 minerals on here, they have different atoms in them that can actually be replaced with uranium. So it's perfectly reasonable for some uranium to substitute into other spaces of similar atomic size. So in the case here, zircon has zirconium in it. It could replace that. In the case of monazite, it could replace either cerium or lanthanum. And all these other different types of cations in this case, or I think it's cations. All of these different types of ions it could replace and substitute into the crystal structure, so it doesn't always have to have uranium in the chemical formula. Sometimes, and actually a lot of times, uranium and other isotopes. Uranium's not the only isotope that can replace things. There are other elements that can substitute in, all based on charges and similar atomic sizes. While uraninite is the only one that actually says it has uranium into it, uranium can substitute in these other places, or in these other spots in different minerals, based on, it's not going to overwhelmingly replace it, but it can. It can replace it to some extent. So, let's keep going here. Now, while I said we do have to be careful when we examine sedimentary rocks because they undergo a lot of chemical and physical weathering, the beauty of it is that certain minerals can be very resistant to chemical and physical breakdown. And so here you can see the greenish tinted mineral is a clay known as glauconite. And in glauconite can actually contain potassium. I don't have the chemical formula up there, but believe me, glauconite can contain potassium. And in this case, if the glauconite is preserved well enough, we can actually use these sedimentary type crystals in glauconite to determine the age of the rock. Or, in this case, the age of maybe these sediments. Once we are able to get radiometric ages, it gives us a great deal of power because we can see similar or identical rocks in different areas of the Earth's surface, and we can immediately know what their age is. And the bonus here is if there's fossils in there, and those fossils have a very limited window of geologic appearance and were widespread all across the Earth, then we can make those fossils index fossils and we can give them an exact age. And if we find those fossils in other sections of rock anywhere else in the world, we know that the rocks have to be of the exact age that the radiometric dating said. But at the same time, we don't have to go back into the lab. We can just say, okay, because these rocks contain this fossil and we've determined the radiometric age of that fossil, this fossil that appears in, well, let's just say we find a fossil in Bakersfield, California, and we radiometrically date the rock layers that that's in. We find the same fossil somewhere in Cambodia. That fossil is going to be relatively the same age, maybe within about, maybe within 1 to 10 million years of the same age. Now, 1 to 10 million years seems like a great difference and like a significant error to be off, but in the scale of geologic time that's so vast, up to 1 to 10 million years is not that bad. And this is brilliant, as the bottom points out. This actually saves your tax dollars because it's expensive to perform analytical experiments in the laboratory and get radiometric ages. Again, a tale from my graduate school. I think we were trying to do some uranium lead dating, and the cost was about $300 per slide, and we had about 40 samples. So it can add up very quickly. So fortunately, this is a method to kind of save lab time, save money, and you want to use index fossils as much as you can. Okay, now we move on to fission track dating. Again, it's fission, F-I-S-S-I-O-N, not fusion. Fusion is something else. You can talk with your physics professor about that, and they'll go into a whole lecture on that. But what is fission? Fission is it's another type of radioactive decay, and in this type of radioactive decay, what's going on is you're basically splitting the atom. We're going to be looking at uranium-238 here. So what's going on is you're splitting uranium-238 into two lighter isotopes of relatively the same size. Now, fission doesn't just happen in uranium. It can happen in other types of isotopes as well. It's usually a lot more, and I don't know if this is fully accurate, but from what I've heard, it's usually more rare than the other types of decay, alpha, beta, gamma, that we've been talking about. But when fission does occur, it splits it into two relatively same size lighter isotopes. In the case of uranium-238, it splits into an isotope whose number I can't remember, but barium and krypton. So it splits into two isotopes of those two elements. And I should clarify that that's the example I'm going to use, but it only happens about 1/3 of the time. There are actually two other ways that fission can divide uranium-238, but we're going to stick with barium and krypton, so that's what we're going to just say happens. Whenever fission happens, not only does it produce barium and krypton, or the two lighter isotopes, it also releases a great deal of neutrons and energy going off, and that energy can be damaging to the mineral crystal that it's entrapped in. So if you look on the right-hand side, you're going to see a close-up of the mineral zircon, and this is very much zoomed in. We're probably looking at a mineral that maybe was up to 3 millimeters in size, so a fraction of an inch we're talking. And what I want you to focus on is there's a lot of dark sections, but there are some very thin linear dark sections that look like scratches on the surface of this mineral. And those scratches on the surface, I'm going to call them scars. Other scientists will call them tracks. What they are is they are the result of all this excess energy from the fission process causing damage to the crystal structure. And the longer the fission has been going on, the longer the crystal has been around undergoing different half-lives, the more of these scars that will pop up. And you'll see that in the next diagram that I have for you here. But basically, millions of electrons worth of energy cause all this scarring. And essentially, the more scars that we have on the surface of a mineral like this, the older it could tend to be, depending on a few different factors. So here you can just see at the very beginning of this mineral's life cycle, we have uranium-230, I gotta go back for a sec, what was it? 238. Okay, several uranium isotopes. I want to make sure I'm dealing with the right one here. So uranium-238 at the very beginning is entrapped within this crystal. It just solidified, but if we give it time, in this case 150 million years, you're going to see the amount of scarring increases, and that's through increased amounts of fission occurring, releasing all those electron energy volts that are causing this scarring to occur. Now, we can use this to measure. Now, this is a very kind of advanced way. There aren't too many geology textbooks that are talking about this, but this is, in what I've read and researched, this has been a very prominent mechanism for radiometric dating in a variety of different new research. So, what will happen here is the scars that are occurring naturally, we will call them spontaneous fission tracks. They're just the scars that are from just leaving the mineral alone in nature, and it's undergoing its natural fission. On the other hand, though, what we can get is we can get something called induced fission track. Now, if you've ever heard the word induced before, you've probably heard it with labor and pregnancy and things like that. If you induce somebody during labor, you're making basically the person force the labor and have the baby early. In this case, we're not talking about having babies, but what we are forcing to happen is we're forcing the isotope to become super excited and super radioactive to cause this scarring to occur again. So this is what we call induced fission. And induced fission, the way it works is we just, in a laboratory, we aim kind of a neutron gun at an isotope and we fire it at it to super excite it and cause it to initiate further fission and scar the crystal more. Now, the technical process here is shown on the right-hand side, and I've even got one in the next slide. Let me just bounce to the next slide just for a minute. This is showing you how things happen. We take our mineral, either apatite or zircon in this case, and we basically polish it down to a nice flat surface. We then take a grain, or not a grain, but a sheet of mica. Mica is a mineral that's extremely flat. It's a phyllosilicate mineral that's very, very flat and has a very low uranium content. And you're going to see why we use that in just a second here. Once it's got the sheet attached, we will then fire that neutron gun at it, and that neutron gun is going to cause any uranium in the crystal to become radioactive and super excited and release more of that electron voltage worth of energy, causing scarring on the crystal. We will then remove the mica sheet, and as you can see in the last picture here, we can compare things side by side. On the left-hand side, we have the original crystals, but now the crystals have been double scarred up. They have the original scars from the spontaneous fission, but it also has scars that's been produced from the induced fission that we just had. On the other hand, though, on the right side, you can see the mica sheet actually preserves just the scarring from the induced fission. So what we can do is we can compare and contrast the two to get an idea of how much uranium is in it. If we bounce back here, you can see the bottom part. We can, through this process, figure out how much uranium-235 is in something, figure out how much uranium-235 is in the crystal. And fortunately, the amount of uranium-235 that we determine to be present is always available is always present in a constant ratio to uranium-238. So we can figure out how much uranium-238 is in there as well. Then we can determine the total number of uranium, the total amounts of uranium in there, and we can relate that back to the number of scars that are appearing on the crystal per per square centimeter. Let me flip to the final diagram because this pretty much shows the whole story. We figure out through this process how much uranium is in there. You can see on the left-hand side there is a chart going from 0.01 ppm all the way up to 10%. 0.01 is parts per million, so it's very, very small fractions of percentage of uranium in a substance, going down to a substance that contains maybe 10% uranium. In the middle, there's little blue strips. Those blue strips represent the mineral we're working with, either zircon or apatite, depending on where you are. Each one is going to have a different type or a different amount of uranium that can be present in there. We can also do it with naturally occurring volcanic glass. When you figure out how much uranium is in there, you will then go and you will count all of the scars or tracks that have been produced. And once you do that, you can figure out how many tracks you are, how much uranium you have, and then essentially trace down to the bottom. So let's just say for something like if we had apatite with 10 parts per million uranium content, we could essentially trace over to the right onto the graph, and let's say we counted maybe 1,000 tracks per square centimeter. We trace over to where we see the band for 1,000 tracks per square centimeter. We immediately go down, and that puts us at maybe an age of about 100,000 years. I'm just doing this through pure sight. If it doesn't line up exactly, it's just for demonstrational purposes. I haven't rulered it out, but it should be somewhere around 100,000 years. Might be a little bit older than that. So this is a way that most textbooks don't talk about. It's a pretty advanced way, but it is definitely a major part of what we do to try and radiometrically date things in science. As I mentioned before, with this type of radiometric dating, as with all radiometric dating, we want to watch out and make sure things don't get physically and chemically altered too much and don't get heated too much. This is one of the trickiest parts of fission track dating. We're working with the mineral apatite and the mineral zircon. And the annealing zones for these, the partial annealing zones, think of it as these annealing zones are kind of temperatures which allow the system to open. It makes it kind of Swiss cheese-like and can allow some of the isotopes, either parent or daughter, to escape and offset the age. So what we want to do is, if we're going to use apatite, we want to try and watch out for apatite that's experienced temperatures between 150 and 230 degrees Fahrenheit. Those are some very low temperatures compared to what the Earth can get, but compared to heat, they're actually very easy to get to. If you look at places in the desert, they can reach 110 to 115 degrees Fahrenheit relatively easily. So working with apatite, you have to be very delicate and really hope you find a nicely preserved sample, because this annealing zone can be reached between 150 and 230 degrees Fahrenheit. So that's essentially the temperature of a hottest day to half the temperature of your oven. You probably bake things in your oven at hotter temperatures than apatite will be weakened at. So we want to watch out for that. Zircon is a little bit more forgiving. Zircon has this annealing zone, or this kind of partial opening zone, from 446 degrees to 626 degrees Fahrenheit. Now, that's probably closer to 446 degrees. You probably bake things in your oven at that temperature all the time, so it's a little tricky to work with, but the other end is at 626 degrees Fahrenheit, which is above what you would cook things in your oven, even on the highest temperature. So it's a little bit more forgiving, but still, on an Earth where there are incredibly hot temperatures below the surface, and sometimes even at the surface, this is concerning, and we need to watch out for these temperature zones when working with these minerals and doing fission track dating. Now I've told you many different ways in which geologists perform radiometric dating. And I've told you all about the perils that can be encountered when you're trying to radiometric date things, but also told you some very neat ages as determined by radiometric dating. So here, you're going to start seeing where the oldest rocks on Earth are that we have radiometrically dated. If you look at this image, this is showing you where the oldest rocks in the entire world are. The oldest rocks on the surface of the Earth are actually located in the Jack Hills region of Western Australia, which is near Perth. They were found just before the millennium in 1999, and the rocks themselves have a very complicated story. In fact, the date that we have this age for isn't even a full rock. It's a grain of zircon. I think it's zircon. Let me just double check here. Yeah, a grain of zircon that was found within these rocks. So the story here is that this grain of zircon was originally in an igneous rock. That igneous rock broke down, weathered, and eroded. It was converted into a sedimentary rock like a sandstone. That sandstone, over the period of its existence on the Earth's surface, eventually got metamorphosed because the Jack Hills region is a metamorphic rock outcrop. So this one crystal, throughout the span of its life, experienced each of the major rock types as it existed so long on the Earth's surface. So the actual age of this is 4.37 billion years old. And I think scientists probably knew about it a little bit before 1999, but they really wanted to make sure they were properly age dating this and get more samples before they said definitively this is the oldest rock. But all those tests came back at this time of recording. 4.37 billion years is the oldest rock on Earth. Now, the interesting thing here is, and I shouldn't even say rock, it's the oldest crystal now in metamorphic rock. The interesting thing here is that with this, the Earth is supposedly 4.6 billion years old, but this single crystal is only 4.37 billion years old. So why isn't it as old as the Earth formed? Well, we'll get into that in a little bit, but there's still possibility we can uncover other rocks on the Earth's surface or just below the Earth's surface that are actually older. Now, let's go to the northern hemisphere. If we go to the northern hemisphere, where are the oldest rocks located in the northern hemisphere? These are actually on North America. They're part of what we call the Canadian Shield, which is kind of like the nucleation point for the entire North American continent as it grew in the past. So you would expect to find some of the oldest rocks here. This rock was basically analyzed. It was another zircon, and the zircon was analyzed using a different radiometric technique. In this case, we were using neodymium samarium dating, and we got an age somewhere between 3.8 and 4.3 billion years old. So this was found just after the millennium in 2001, and it's located up near Hudson Bay in a greenstone belt, which is another metamorphic belt. And I don't even want to pretend like I know how to pronounce that. Nuvvuagittuq. If anybody's from Canada, let me know. But anyhow, up near Hudson River in Quebec, this is the place that has the oldest rocks that are in North America. Other older rocks, that was the oldest rocks in the northern hemisphere, not even just North America. Another old section of rock that we have is actually just recently found in 2016 due to glacial melting. Glacial melting can have pretty bad effects on the Earth, but this is actually one time it did allow us to see something positive. It allowed us to see these rocks here. These are from the Isua Greenstone Belt, which is located in Greenland, southwestern Greenland, as you can see on the map there. And what you're seeing here are examples of rocks with fossils in them. And the fossils in these old rocks are actually stromatolites. The same creature that was featured on the title slide fossil is actually shown here. The difference, though, is that these are the oldest stromatolites we have found in geology. When we did the aging of these rocks, they dated, I think, the stromatolites here, and they turned out to be 3.7 billion years old. So in this case, they didn't really go after minerals. They looked at the species and the fossilized life in there. And so 3.7 to 3.8 billion years old are these rocks. Not as old as the rocks up by Hudson Bay, but still very, very old. This puts the rocks back in the Archean section. If we look at the rocks from the Jack Hills region, that puts those rocks, I think, either at the very beginning of the Archean or possibly during the Hadean. You saw the Hadean and the Archean very early on. The Hadean was that hellish landscape with oceans of magma and things like that, and lots of meteorite impact. The Archean was following that up. It was a Precambrian period where we had just somewhat gotten water on the Earth's surface, but there's still a lot of volcanic activity and not much life except for the stromatolites that were in that picture. Now we beg the question, well, that's the Northern Hemisphere. What about the USA? Where are the oldest rocks here? A very good question. The oldest rocks that we have in the United States are actually located in Minnesota. So if you're from Minnesota, you may have seen some of these places. They mainly outcrop in a place called Morton, and so it is actually known as the Morton gneiss, and you can see actual samples on the right-hand side. Now, we have looked at gneiss before. Gneiss is spelled G-N-E-I-S-S. And we looked at it when we were talking about different types of rocks, opening our eyes to geology. Metamorphic rocks were those that got reintroduced to heat and pressure, and gneiss is reintroduced to a lot of heat and pressure. So much to the point where the minerals start to segregate and form specific color bands within the rock. And if you look closely, you can see that pinkish colored banding and gray colored banding and maybe even some white colored banding shown on these rocks here. If you can't see it, don't worry, I've got a much closer up slide in the next section here. When we look at the age of these rocks, though, these rocks came back after dating. We found more zircon crystals in them, and the dating shows them to be 3.5 billion years old. So the oldest rocks in the United States are 3.5 billion years old. Again, putting it into perspective, the oldest rocks in the world, 4.37 billion years old. So, very, very old rocks, and you can see actually where they outcrop in Minnesota in the upper right-hand side here. I do also want to say I think there is a very small sliver of northwestern Michigan that might also have these. But this makes a lot of sense given what I just told you with the Canadian Shield, what we call a craton, the nucleation point that our whole continent built off of. This is probably the outermost extent of the Canadian Shield that just kind of bleeds over a little bit into the northern part of the United States, and basically most of the United States kind of formed onto this shield later in life, onto this craton later in geologic lifetime. So very sensible that these are all the way up there. Here are just some examples of ways that people have used the Morton gneiss. It's amazing where it pops up. On the left-hand side, the city or town of Morton actually made their welcome sign out of the Morton gneiss, and you can see the gneissic banding there a little bit better. It's really crazy when you think about it, because this gneiss here, or this sign, is basically billions of years old when you think about it. It's pretty crazy. You know, the city was established in 1884, but the rock was established billions of years ago. If you go down to the left-hand side, that is a church within Morton, and the cobblestones that they used to piece this church together were of the Morton gneiss, so you can see it there as well. Interestingly, if you go to St. Paul, the capital of Minnesota, far from Morton, they've delivered some of the Morton gneiss to locations there. There is a building on the lower right-hand side, which was, I believe it used to be a telephone company or an electric company, and now it is a bank, but the face of that building is made entirely of the Morton gneiss. And up on the right-hand side, outside the Minnesota State Capitol building, you can see this statue here, and at the base of this statue is the Morton gneiss again. So this base is of billions of year old rock. If you're wondering who the person in the statue is, and you're a football fan, you know that Minnesota's football team is the Vikings. The character on top of the Morton gneiss outside the state capitol is actually Leif Erikson. Here is a close-up picture of what the Morton gneiss looks like, and you can see beautifully here all of that gneissic banding. The black minerals banding together with themselves, the whitish minerals kind of coming together in layers, the pinkish minerals coming together in layers as well. classic definition of gneissic banding through the reintroduction of heat and pressure causing all of this. If you look on the left-hand side, though, you'll see that somewhere in Morton they do have a plaque stating that this is the oldest rock in the United States. However, there is a slight problem. I'm going to give you a couple of seconds. Take a look at that plaque and see if you can identify what the problem is. Okay, so basically the problem is this. They made the sign probably way early on, and we've made lots of technological advances since. They've got the rock being 3.8 billion years old. If the rock was 3.8 billion years old, it would be, what did I say this was? Hold on, I gotta go back. That would be 3.5. So they've got it about 3 million years older than it actually is. I don't think they did that on purpose. Again, it was just technology at the time, probably said 3.8 billion years, and since refined technology has said actually it's more like 3.5. So 3.8 billion years is not correct. It was I even had the number there, 3.5 billion years. And you can also see what I'm talking about with the error measurement there. In this case, it's plus or minus 9 million years. That seems like a huge portion of time, but when you're talking something with an age of billions of years, that error is a little bit more acceptable.